title a little bit, largely because of what's on my mind lately. So I'm going to talk about plastics in general. And the first question I wanted to ask was, any of you know what a polymer or a plastic really is? No? So the word poly means that you've got, half the word that's poly means that you've got lots of something. And the mer is a little bit less obvious. If you take any molecule as a building block, a mer, I like to use these little beads that I stole from my 4-year-old as my mers. Right? So if you think of, say, any material you're used to think about, say water or hydrogen or any atom or small molecule as my bead, then a polymer is basically just the idea of snapping all of these guys together. Now remember, this is chemistry, not making necklaces. And I make a long chain of them. Right? So for instance, one that's, say, 100 mers long, and that's what I call a polymer. Okay? Now the neat thing about making polymers is that when you make molecules really long, all sorts of neat things can happen. For example, these guys can tangle up with each other. Right? Nope, that one didn't work so well. But I can get a tangled mess. For instance, think about a bowl of spaghetti. Right? If you let a bowl of spaghetti cool on the table and all the little chains get locked up with each other, it's actually fairly hard to pull one out. Right? And that's part of what gives you the really neat properties of polymers. So how many of you remember playing with this stuff as little kids? This is Silly Putty, for those of you who've never seen it. And I'm going to remind you of some of the tricks of Silly Putty. Okay? Silly Putty gets a lot of its properties because it's made out of all these chains that are entangled together. Right? So if I act on it really slowly, those chains have a chance to unentangle from each other, and it acts kind of gooey, a little bit like a liquid. Right? And let's see if I can do this fast enough. If I act on it really fast, it snaps as if it were a rubber band that I broke. Okay? You can send that to even more extremes. What's going on here is that those chains don't have a chance, like spaghetti, to get apart from each other, and it acts like one big mass. So if I roll it up into a nice little ball, it bounces. Right? And if I were brave enough and thought you guys would return it, you can actually bounce it across the room. Right? It's really kind of a cool material. So I'll let you guys play with it. The other neat thing about this one I rolled up, some of you saw me roll this up right before I started the lecture. It's had a chance to sit here, and it started flowing. Right? And by the end of the talk today, it'll be a nice little puddle on the ground. And all of that comes from the fact that the polymer chains are very long and can entangle with each other. The other neat thing about these polymer chains is that you can make them in a lot of different ways, right? Since I'm going to talk about repeating one bead after another bead, I can make something that's alternating, right? Put in orange and blues in this case and get a lot of tunability out of it. I can make, this is what I call a block copolymer. It's got a red half and a blue half, and I can use that to my advantage to design really neat properties. So I was going to do a little bit of show and tell up here about a few things that you might be able to do with them. But before I start, I gave away some bead sets to people earlier. Who has them? Okay, I would like a couple of them back to show something. Right? I gave them purposefully. Do you want to hold it up really high to stand up? I gave away bead sets that were more fancy than mine. And what you're seeing here is that there's almost infinite tunability. Right? These sets had, say, 20 or 30 different colors in them, and every one of these necklaces is different. Right? So not only can you design a polymer with different properties, if I make a whole lot of polymers, say this guy contains probably many, many thousand polymer chains in it, each one might be slightly different from another one. And what I get out of it is the properties of all of those guys mixed together. Okay? You can keep the necklaces. Okay, so let's talk about some of the modern marvels of this age. As Mark just told you, I have little kids, so I use a lot of these. Okay? Has anyone ever tried to cut these open? Do you know what's inside? I'm looking at a couple of the people in this audience who look like they might have kids. Ever cut one open? No, you just put them on, took them off, and threw them away as quickly as possible. Okay, so modern marvel of polymer science. These things you can put on a baby at, I don't know, 7, 8 p.m. And when I wake up in the morning and go pick up my son and change his diaper, this thing weighs like 5 pounds, right? And I'm thinking, how in the world does it do that? So I'm going to take out the stuffing so you can see how it works. Because it's certainly not just the plastic coating that does it. Are we having AV problems?
No, we're going to get some light on it.
Okay. Okay, so it looks like cotton, right? It looks like cotton balls, completely non-toxic. Clearly I put it on my kids. Taking all of this out to put into the beaker for you guys. I feel like I'm on a cooking show, except I wouldn't suggest eating this. Okay. So I'm getting off as much as possible so you can see it. Okay. This is a polyacrylic acid. So if you think about it this way, and it's a salt, every single bead on this polymer chain can hold on to some water. And all the chains are nicely tangled with each other, so it doesn't just dissolve and make a water solution. Let's do this. You see how it's just absorbing all that water? I've put in probably about 10 times as much mass as the polymer had in it already. And it just keeps taking it up. Can you guys in the back see this? No water left. I'll put in a little bit more. And then I'll let some of you guys up front touch it. I dare you. It feels slightly wet, right? But it's holding on to the water really, really well. Right? And that's the whole point, right? We actually use cloth diapers on my kids quite a bit. And those just that hold up the water next to the skin, these guys absorb huge amounts of water, and it's the reason that they don't leak, right? Unless they fail. Anyone else want this? It's a really neat use of these kinds of polymers. So I don't want to leave you with the idea that all plastics are these kinds of things that fill our landfills. It turns out that a fair amount of biology is also polymers, and therefore so is a lot of food products. This came out when I was in high school, so I've been holding on to this bottle for a very long time. I won't tell you how many years, but for whatever reason there was a time when people thought it was really neat to drink clear liquids with dots floating in them. Don't ask me why. And so you're looking at this, and can you all see the dots? They're all floating in there really nicely. Anyone have any idea how they did this? It's not density matching. If it were density matching over the last 20 years, all of those dots would have fallen, right? What's going on is they've made the sugars that are in your soda, that make your soda taste good, locked up with each other a little bit so that they trap the dots in the liquid. When you drink it, you can't taste it in your mouth, you can't feel it, but all the dots are stuck there, right? And you can tell, I'll leave this up here so you guys can play with it at the end. If I spin the bottle, how many of you think that the dots will keep rolling around, keep spinning with the direction of flow, right? That's how it should work. Because this polymer network is holding those dots in place, they spin and spin and spin like I turn the bottle, and then they recoil, and they come back to where they were supposed to be. It's really kind of bizarre. I'm not entirely sure why anyone ever drank this, but you can buy, each bottle of this stuff is now worth something like $40, $50 on eBay. And I think it's all from people like me who are using the lecture demos. Okay, so the main point of this is that when you make long polymer molecules, you get a huge amount of tunability out of it, and you can get designer properties. The other piece of this is that you can do it fairly cheaply because everything up here is either a byproduct of plants or a byproduct, not a product, but a byproduct of making petroleum. So when you make petroleum, you pull out all sorts of little other things that come up in your crude, and you turn some of it over into gasoline, and then what do you do with the rest? Well, it turns out that you make polystyrene bottles, you make polyethylene bottles, you make diapers. And that's part of why plastics are so cheap. And you can make all sorts of other designer tools and designer materials. Okay? So what I've kind of shown you is stuff you probably had seen but not really figured out, okay, why does it do what it does? What I want to talk about today is the basics of, okay, so these are what I call the diaper polymers. They're very basic. They're used to make things that you buy in the grocery store all the time. And the main difference here, this is ethane, which is just, for instance, one of the things you pull out with crude oil. And it's just two carbons, and there are two electrons shared between these two carbons that make that bond. Okay? This is polyethylene, which if you use plastic containers that are labeled LDPE or HDPE on the bottom, that's recycle codes 1 and 2. And that's this molecule. So you've just taken those guys, that's your mer, and you've strung them together. right? And most of these kinds of polymers have 100 or more repeats, right? So it's a long chain of these molecules all strung together, okay? Now, where I'm going with this, I'm going to skip that for a second, is that that's this guy. And this discovered maybe 50 years ago. So it's actually not that old a field, this whole idea of polymer science. And we use this a lot. High density polyethylene is this cloudy stuff. It's used in a huge number of different bottles because it's chemically inert, it's really strong, you can drop it, it's not going to break. Low density polyethylene is much more flexible. So most of your plastic grocery shopping bags are made out of this, also some of your CD cases because it's transparent, okay? Where my research really fits into all of this, and I think where a lot of new nanoscience is coming in, is going from this molecule to this one. Okay? Now just looking at it, the main difference here is if you look at these two carbon molecules, or carbon atoms, sorry, here they're connected by only one bond. Here they're connected by two. Okay? And what that led to is polyethylene has a conductivity of pretty much nothing. Right? And you don't want it to. You want all of your plastics to not conduct electricity so you can use them as insulation on your wires. You want them to not conduct heat so that you can use them in your oven mitts, etc. All of these things, we use that property a lot. If I put in this double bond here, I can tune its conductivity all the way up to that of copper. Right? And that gives me a huge amount of extra tunability to make materials that are not on this table. Right? To make new things and new applications open up. So let's talk about how that happened. So I write it this way, where these brackets mean repeating, right? If I draw it out, what polyacetylene, this conducting polymer is an alternation of a single bond and then two bonds, single bond, two bonds. All that means is that here, if you imagine a carbon at every interstices, I'm sharing 2 electrons, 4 electrons, 2 electrons, 4 electrons, okay? Now, because this polymer chain has 100 repeats in it, this is nearly the same as moving each one of these double bonds over and making it 4, 2, 4, 2, 4, 2 instead of 2, 4, 2, 4, 2, 4. Okay? And I can do that lots and lots of times. What you realize is that when I draw this alternation in a really long chain, it's a lot like saying I have 1.5 bonds everywhere. Right? And what that means is that I have 2 electrons shared between every set of carbons, and I've got this extra set of electrons that's kind of free-floating along the chain. Right? Free-floating electrons can move. Right? And if you think about kind of the simplistic example of how do metals conduct, you think of them as having a whole lot of electrons that are just floating around, and they can move across your material. That's what's happening here. I've created a situation in which, even though most plastics are insulators, I've got electrons around that can move back and forth along the chain or between chains, and that allows me to conduct electricity. Okay? And it turns out that I can make a lot of polymers that have that double single alternation, so they all conduct electricity. But the really neat thing about chemistry is that unlike, say, gold or silver or even silicon that I dig up from the ground or purify some way, I'm making these, and I can create a whole lot of different kinds of polymers. I'm showing you kind of a set of 8 here. Each of these polymers is a different color, right? If I put charge on it, it emits a different color of light. Right? So I've got a huge amount of tunability. So I can start to make polymers that are tuned, just like all of these guys were tuned for various absorption or mechanical property situations. I can tune all of those guys for a lot of different semiconducting or microelectronics applications. Right? And that's really where I think this whole field is going. So I was going to give a few examples. That's too dark, and there's probably nothing I can do about it. So I was going to give some examples of where you might use this and then talk about the kind of science we do. So for example, this is supposed to be a lantern. So the easiest way to create light is to burn something. I guess you could burn a plastic, but I wouldn't recommend it. So this is a kerosene lamp. And around 1870, a number of people, Thomas Edison included, but not actually the first one, invented incandescent lights. Right? So the idea here is actually not that different than burning something. They take a filament that's fairly resistive, and they shove electrons through it. They can't all make their way across, and they emit light instead. Okay? Not very efficient, but it works very well, and it's what many of us are still using. This room is filled with fluorescent lights. This is actually really complex chemistry. There are 2 electrodes at either end. They form ions going across this thing, and they arc a plasma from mercury. The important point here is that this is actually very efficient. If we switched all of the lights in the country to fluorescence, we'd be done. The problem is a disposal one. This little drop of mercury is the way we get the light out of it. And disposing of mercury, as you may or may not know, is really, really difficult to do. And right now we're not necessarily taking care of the problem. So you're starting to see these kinds of lights come on the market. These are light emitting diodes. Actually, the first place that most people saw them were in the brake lights of their cars and then in Christmas lights, right? They are very small, they're solid state, they emit a huge amount of light, and they're not terribly efficient, but they're much better than this guy, right? But one of the problems with these, just as an aside, my husband actually makes these, so we have some internal competition at home. These guys, the problem is that they're made out of mostly gallium nitride, gallium arsenide. These are fairly expensive, fairly non-earth abundant materials, and they are generally point lights. So the idea of making a brake light out of them or a Christmas light out of them makes a lot of sense. To make something that plugs into what's called an Edison socket, the thing that goes in your ceiling, you have to come up with some strange design where you've got a lot of these arrayed, right? So what I wanted to show you was how you might make these out of a polymer, okay? Can you see these movies at all? Raise your hand if you can see them.
I could turn off one more light.
Let's see what we can do.
Stage 4 there.
Okay. Well, let's see what we can do. And I'll try to describe it a bit as best I can. So the idea of these plastics, whoops, is that you can process them the same way you process all of these guys. So you've got a lot of infrastructure in place to make plastics. So this is a movie from the University of Wisconsin. What you're seeing at the back here, if you can make it out, is the fan from a CPU. So they took apart a tower computer and they took the fan out, okay? And they're going to put onto that a glass microscope slide that has a conductor already on it. So we can start my movie. Okay, you see that happening? There we go. So they're going to put on that glass slide. They're going to smear it with the polymer. It's one of the ones I already showed you, actually. You're just using a Q-tip. Now you want your polymer to be pretty smooth, so it emits kind of continuous light. So you're just going to put this is just a bottle around it so it doesn't spray all over the room. And then they start the fan so it spins. And as it spins, it flings the polymer out and smooths it onto the surface. Okay? They're going to do it again. And then they just come and put little pieces of aluminum foil onto it to act as the other electrode. And they come by with a little bit of voltage and turn it on. Right? And you see it's not 100% success yet, but they're getting light out of about 50% of their little devices. This was actually made in a high school chemistry lab. Okay? So it's dead easy to do. And that kind of indicates to you that this might be something we can make in very different ways than we're used to. So let me stop my movies. So the idea here is that if you can just take your material and smear it onto a surface, you can start thinking about making your devices in ways very different than we're used to thinking of. For example, if you remember, Mr. Rogers used to take trips to various factories, and the way one puts together a computer chip is just very, very different. Making these kinds of polymer devices may be actually more akin to making newspaper. So if I make newspaper, what I take is a giant roll of paper, and I send it through a press where I deposit different amounts of ink of different colors onto it, and at the end I get a full-color newspaper. What I do in order to make a light-emitting diode in the future might be to take a roll of a flexible backing, and then to deposit onto it my polymers that are going to emit the light, and then roll it up at the end. What this implies is that your device, your light or your display, may have a lot more properties more like newspaper than like your standard light bulb. For example, it might be flexible, right? It could be lightweight, and it could be really large area, right? So what might I do with this? And here I'm just going to take you on a tour of some products actually on the market. So this is a purse that was on the market in 2003. I didn't buy it, and I really wish I had. So I don't know about you guys, but whenever I'm walking to the dark, walking in the dark to my car, my keys are inevitably at the bottom of my bag, and I'm standing at my car in the dark feeling for my keys at the bottom of my bag, and I can't find them. The idea of this purse is that the inside lining of the purse was one of these light-emitting diodes. Okay? So you opened your purse, and the inside of your bag lit up, right? And then you could find your keys easily. You could never do this with a normal light because you actually needed the whole lining to light up, not just a point source like a little light bulb on the side. It's a very low power, so it could run off of, in this case, a very small watch battery hidden in the lining of the purse. And it's fairly long lifetime, so the light lasted as long as the purse did. Okay? It's a really neat application, and could only work with these kinds of light-emitting diodes. The other idea, that was a small application. This is a prototype of a very large application. If you can make wallpaper that lights, you start thinking about interior design in a very different way. Instead of, for instance, this room, someone, I'm going to put it up at the ceiling, someone thought really hard about how to do the lighting so that you guys get enough light that you're not falling asleep, and I have enough light that I can see you. So you see that there are all of these point sources, and they're arranged in a aesthetically appealing way. The idea now is that I can use wallpaper that's like light, and I can create things like false skylights. I can create entire walls that are kind of mood lighting. I can change their color, I can change their brightness, and I can tune them the way I want them to be tuned. So it changes the way we think about design very much. These are actually on the market. These are displays made from polymers. The idea here is that first they're much lighter weight than your normal display. Your normal LCD display actually has a little bit of liquid crystal in it, which is the LC of a display, that has a lot of pieces of glass that are polarizers and other things. As I showed you when we made a polymer light earlier, you tune the color by tuning chemistry. So you're actually going to make something that emits the right color right away. You just tell which colors to light up at the right time. So you can get millions of colors, you get really nice clarity, you get incredible brightness because you don't have all those other pieces there, and it turns out you get lifelike motion. So Samsung has one that was on the market last year. So these are kind of the new kind of display that I think we're going to be seeing coming up a lot. But it's not actually taking advantage of all of the properties of the polymers. These are prototypes from Universal Display that's in New Jersey and Sony. The idea here is that, and I put away my iPhone. So your iPhone is really cool because it's a little tiny display that fits in your pocket, right? What if it looked like a pen and you pulled out the display and the touch screen to use when you needed it to. When you were done, it retracted back into the pen, you put the pen back in your pocket, right? When suddenly you don't need a hard backing, all of the size issues go away, and also some of the durability issues go away. I've dropped my iPhone so many times I'm a little scared, right? These guys are much more durable. So this is Universal Displays. Theirs is actually exactly that idea. This is a GPS system that retracts back into the pen. This is Sony's, and they're showing it winding up around an axle. They haven't come up with what they're going to make with it yet. Okay? But these are kind of all new ways of thinking about lighting and displays. This is the last one. So this is, again, the idea of infinite area, the same idea I talked about with lighting. There's no reason you shouldn't be able to do that with a television also. So if your display is like wallpaper, you print one out that's the size of this wall, and when I want to turn it on, I turn it on, and when I'm done, I turn it off, and maybe I turn it into a light, or maybe I just turn it back into a wall. Okay, it's kind of a neat idea. Okay, so displays and lighting are actually already on the market in many places. It's largely the playground of industry at this point. As an academic and lab scientist, what we tend to do is we tend to work on the things that are a little bit further along the pathway. So I'm actually very interested in polymers for renewable energies. And the main reason is that I think in this series and probably out in everywhere, you're hearing a lot about how our general makeup of fuel in this country is about 85% fossil fuels of some kind, natural gas, coal, and petroleum. We burn them, we get heat, we convert that into power. Renewable energies is actually only about 7% of the total pie, and although you hear a lot about solar, particularly in Berkeley, it's only 1%. It's a teeny tiny piece of the way we're generating electricity right now. And there are a lot of reasons for this. It's not a supply problem. We have a huge amount of solar energy on Earth. So we generate we have 4 orders of magnitude more solar radiation than we have electricity usage. So we have a huge supply of solar energy. We have a couple problems. One of them is that silicon solar cells, the solar cells you're used to seeing, are actually fairly expensive. They're heavy and they're difficult to install. Particularly in California, if you want to install solar cells, normally what you have to do is change the structural supports of your roof, because your roof is not meant to handle that much weight. Right? There's just a significant barrier to installation. And the idea behind polymers is to use the same newspaper idea, but now use it to make a solar cell. So we again have a newspaper type press with a substrate. We deposit the electrodes, the material that generates our electricity, and we're able to roll it up and use it as if it's wallpaper. Okay? This is from a company called Kanaka. This is their product, and you can see it coming off of their roll-to-roll processing right here. Right? So making giant rolls of this stuff. The copper-colored stuff is the solar cell. Okay? And they've got a few things already out there that you may have seen and not recognized. So this is their module with its little power output right here. The first application was using that to power a iPod or an iPhone. So anyone can just roll this up and put in their backpack. This is at their headquarters. They've got it on the umbrellas outside their cafe, so they can power their cafe with it. These are the windows of their building. This is kind of exemplifying why it's so easy to install. The stuff is somewhat transparent, so they just put it on as a window film. It didn't take any extra infrastructure to install it on their building. This is actually from San Francisco. Has anyone seen these bus stops? How often do you go to SF? It's a smattering of people. So San Francisco redid all of its bus stops so that they have, at first all they had was this wavy red thing on top. They then went and put Kanaka's solar cells on top of that because it was really easy to install, and now it powers the display that's inside the bus stop. So if you're standing in one of these bus stops, you can tell when the next bus is coming. You can actually play video games. It's a very neat application. So if you go to San Francisco, there are a large number of these in the touristy areas right now, so it's around the Embarcadero. But they're slowly doing most of the city in them. So it's a nice new application, and it's already out there. The idea behind all of this is niche power generation. The idea is not to create a solar farm like you would with, say, a solar cell, but to create energy where you need it and to try and take some of the load off of the grid. Okay? This is my favorite application because I actually intend to buy this bag at some point. This is, again, Kanaka's solar cell, but it's now on the outside of a laptop bag. Right? And you see there's a little plug that comes out of it, and you can use it to charge your iPhone on the fly, charge your laptop on the fly.
How much is it?
$100. Hint, hint. I showed this to my husband last night. I need a birthday present. So anyway, so you're getting an idea that these are a different kind of application than we're used to thinking about. So you might be asking, okay, you've shown me a few applications. Why are they so niche? Why are they so small? And what I wanted to spend the rest of our time talking about was why is there science on this? Where are we still working? So the key material property, the ability to conduct electricity, is what makes all of these applications possible. A Nobel Prize in 2000 was for the ability to make plastics conduct electricity. So we've got that in place. The rest of this is how to make it optimized, how to make it so that we get enough efficiency to make it worth building a laptop bag or enough power to power more than the display in a bus stop. So in order to go into this, I have to explain how these devices work. Okay? So this is kind of optimized. I'm going to take two materials, two plastics, and I'm going to use them in a solar cell. So what happens is my light hits the solar cell. My light forms what's called an exciton. It's an electron and a hole that are combined. And that exciton kind of wanders around a little bit. In my plastic, it can't do anything more than wander around. Right? Then it finds an interface with the other material. And the other material pulls the electron off and creates two separate charges. Now my charges can move through and go to the electrodes. And then they can be gathered. So the thing to remember here is that charges moving is what we call current, right? And that's your power. So in order to make this whole thing work, I had to have a very concerted thing happen. I already told you I had the materials that absorb light and create those electrons and holes. But I have to create a situation in which I get my electron and hole to separate, and then they can go back to their appropriate electrodes. If I can't do that, those three steps very well, I won't have very high efficiency in my device, and it won't work very well. So a lot of what's been going on now is how do I optimize this? How do I make it so that it will work? So I want to show you a couple of geometries that have been tried, some of which work, some of which don't. So this is a solar cell that has a red layer that absorbs your light and a blue layer that pulls the electrons off. Now it turns out that that thing I called an exciton can only wander around for about 10 nanometers. Right? So that's where Nano comes in. So it can only separate if it's right next to this blue layer. So even if I create light throughout this red layer, only light that hits right in this little cross-hatched area actually works. Right? The rest of it is lost. So then you end up with a manufacturing problem. Okay, now how do I make something that has more interfaces, more red-blue connection where I can separate those charges from each other? Well, I could do something where I try to get them to form droplets or whatever. Now the problem is that if I put red over here and blue over here, my electron goes into this blue dot, but it has no highway to get back to my electrode. It gets stuck in that blue dot. It's like if I were standing on an island in an ocean and I can't swim. I have no way of making it back, and that's another loss. So it turns out what everyone wants is this structure, where I have highways through which my charges can move, and I've got a large amount of interface so that my red and blue always find the correct charges and pull them apart, right? So I've actually set up a really difficult manufacturing question. I need my materials to be pretty thick so absorb a lot of light, but they have to be patterned on the 10 nanometer length scale in a really intricate way. And so what I wanted to talk about was a little bit of the length scale problem and the manufacturing problem. That suddenly I need to be able to control a lot of length scales at once, right? And what I kept saying was that the interaction of light with my material is right in here, right? So I have to be able to control 10 nanometers. Through chemistry, I can get at the angstrom. That's the carbon-carbon bond. It's the way I make the polymer that has all the tunable properties I want. But now I need to be able to control something that's about 2 orders of magnitude bigger. And this is a really tricky length scale because it's about 4 orders of magnitude smaller than a human hair, or even the way I make a silicon chip for your computer. So we have to think really hard about how do I make this happen. So I was going to talk a little bit about manufacturing. How does the length scale affect the way we make something? So this is a Citroën, which is a French car. How do I put this together? If I wanted to make a car, what's the general manufacturing technique I use? Assembly line, right? So I have a car going through, and I have people doing the same thing on every car, trying to do it quickly and efficiently, right? And I'm not sure if you can see it in this lighting. I'll try this again. This actually has a minimal number of people and a large number of robots because they're trying to do this very, very precisely. They want that key hole to end up in every door at exactly the same place. Okay, so it's all about efficiency, scalability, meaning being able to make a large number of them and fairly precisely. And that's on a length scale way up here, right, which is where we were manufacturing things. We've been manufacturing things for a very long time. Microelectronics are actually micron electronics, meaning their size is about 10 to the minus 6 meters. To give you a sense of scale, that's 1/100th of a human hair. And it's 1/10 the size of a dust particle. Okay? But we know how to make 3D, really intricate devices out of this. This is an RFID that is implanted in a lot of your cats and dogs' necks, so that if your cat or dog gets lost, they can find it again. That's all made via this technology. So are all the chips in your computers. And these required new processing techniques, new assembly techniques. The idea being, if you can't touch it, how do you put it together? In the assembly line, we could touch things. Here, we can't touch them, but they're about the length scale of light. We can see them, right? So we use light to make them. So this has actually got polymers in it too. If we're going to make something like this, we take silicon, we put polymer on top of it, and then we expose portions of the polymer to light. And that changes the polymer's properties and makes it so you can rinse it away. Okay? So you rinse away the polymer and you end up with polymer or plastic patterned at a micron length scale. And then you can deposit, say, a metal or a wire, whatever you want, in the parts that are open. And that's how you get these kinds of patterns. Right? That's how you build up the micron scale patterns that are your microelectronics. Now, the little hidden thing in here is that this length scale was about a micron. As I said, that's a fraction of the size of a piece of dust. So if you have dust in your room when you're making these, this whole thing is useless. Right? So how do we do that? That's why we create clean rooms. Right? And that's why people wear bunny suits in those clean rooms, is they're trying to find ways to keep the dust or dandruff from your hair from getting onto the devices. They're trying to keep the fibers from your clothing from getting onto the devices. Many of them are actually filtering your breath to keep the particulates in your breath from getting onto the devices. And it's all just because the dust is much bigger than the thing you're trying to make. Okay? Now, what I'm trying to do is to pattern, so that was up in here. What I'm trying to do is pattern down in here. Right? So now I'm at a scale where I can't touch it and I can't see it. Now what do I do? Right? Well, the simple answer is I've got to convince it to do what I want, right? And that means using that object's interactions with the things around it to make it self-assemble. That's all self-assembly means, is that I've used some interaction to make it do what I want it to do. And so I went and pulled some pictures off the internet and other places of natural things that self-assemble so you get the idea. So this is actually my favorite example. These are penguins. Okay? Now, penguins self-assemble. The idea here is that these are emperor penguins. It's really, really cold, and they want to huddle together to be warm, but they can't huddle together too closely because then they'll start to squish each other. Okay? So what they actually do is they pack into a hexagonal pattern so they get maximum packing and maximum body contact without squishing too hard. Okay? So what does hexagonal pattern mean? It means that they're forming these really nice rows in various directions. Each penguin has about 6 neighbors, right? Because that's how they share body warmth the best. It's actually a very nice idea of attractive interactions. They want to get close together, but there's a counterbalancing repulsive interaction because they don't want to be too close. And that ends up with this happy medium, which I call self-assembly. Okay? So penguins, obviously a much bigger length scale, but they do it. This is my daughter's favorite example. These are hot dogs, and they're cut to be about 1 centimeter thick, and they're floated onto a pan of water, right? And you notice that these guys are packing into a really nice array. Right? You see that each hot dog has 6 neighbors, and you can see lines going through it like this. Right? What's going on is that there are some capillary interactions between these pieces of hot dog that force them to pattern. Yeah, they're just floating on water. This actually happens with cereal too. If you eat Kix or Cheerios, how many people have ever done this? When you end up with just a few Cheerios left, they cluster on the top of your bowl of milk, and they form very nice little patterns. It's exactly this interaction. So last night I was trying to take pictures of this. I didn't realize we'd have a projector. So I had my daughter eating bowls and bowls of cereal, taking pictures of little rafts at the end. It turns out the hot dogs do it better. But you see this all the time because these are different kinds of interactions. So these are the very simple ones. We have a lot of different things at our disposal. So I was going to show you a couple of movies of, of different kinds of interactions. Whoops. Oh, okay. You all have to watch me log in so you can see the YouTube videos. Now you all know exactly how long my password is. Okay. Let's try that again. Okay, so these are little magnets floating in a tub of water. The orange ones are polarized up, and the black ones are polarized down. So remember, opposites attract. The orange ones don't want to be next to each other. The black ones don't either. So they very quickly self-assemble. They realize that the best pattern for them is to go orange, black, and make a checkerboard, right? And it takes about 30 seconds for them to form, in this case, little checkerboards. And it happens over and over again. So you're going to see the guy who made this come in and shake it and separate all those guys off to show you that no matter what the starting configuration is, they come back and make a checkerboard again. And this is kind of the very basics of self-assembly. You've told the magnets some ground rules, some boundary conditions. You go up, you go down, and then they self-assemble to find the pattern that's in what I call the lowest energy, the most stable configuration, and they'll do it no matter where we started. Okay, so now you're seeing them trying out all sorts of configurations, and eventually, right, see they found something that's kind of a metastable state, whoa, and something that's kind of close, and then they keep rearranging until they find the best one. Okay, so that's how self-assembly works. I want to show you one more movie. You can watch that over and over again. But okay, so I'm actually going to pause this one so I can tell you what's going on. So we'll go back to this for a second. Okay, I'll show you, just a second. So I've shown you some pretty toy models, right, that we can tell materials to do something. And in this case, we made a checkerboard. There are a lot of other neat things you can do. So for example, have you all tried to make a box via origami, where you take a pattern or a piece of paper and you try to fold it to make something else? You can use interactions between different materials to do exactly the same thing, which is what these people have done. They made a little, it looks like a crucifix, a series of little boxes, and they made the edges between the edges between the different faces flexible. So you're seeing the little crucifix here. And this is actually nanometer scale, and it's in water. So they're shaking it and bubbling water through it to try and get it to move a little bit and sample different ways of going. And these black sections, oh, I need to stop doing that. The black sections are the flexible glue they put between the layers, between the different boxes. And okay, so you have to be a little patient, and they restarted this thing by accident. there are a lot of jokes about if IKEA could figure out how to do this, we would all be out buying IKEA furniture all the time. Okay, so now you see this side start to fold up, right? Just because it's flexible right there. They haven't done anything else. No one's pushing it. Then all the other edges come in, and it forms a box, right? It's kind of a neat example of self-assembly. I'm not entirely sure what you use this for, since it's too small to be a coffee table, but it's a neat idea. Okay, so then I go back to my little table of show and tell here. What I do actually isn't trying to use more mechanical things like that to build self-assembly. What I do is I try to do it via chemistry. So for example, the interaction I use the most is phase separation or demixing. So if you take two materials, in this case I'm going to use milk and Red Bull, that turn out to be really, really different from each other, they'll separate. It's kind of like oil and water, but it turns out that oil and water is a really bad example because oil and water separate into oil and water, right? 100% oil, 100% water. For many applications, that's not quite what we want. We want something that might be 75% oil on one side and 25% oil on another, or a much larger degree of tunability. So I'm using Red Bull and milk to show you this. So what these guys are doing, you're starting to see it at the bottom here, if you can see from the top of the room, is you're getting a yellow phase at the bottom and kind of a white cloudy phase at the top. I don't really want to pick this up. This whole example made me decide that we need to ban Red Bull. But it's one interaction that we can use very, very easily to control how things self-assemble. The fact that many kinds of materials don't like to be together. So, and that's actually the interaction that's used the most to make photovoltaics, particularly organic photovoltaics. So what one normally does is they choose a red material. I'm just showing you some chemical structures of red materials. These absorb light really well. They blend them with a blue material. So think of this as milk and this is Red Bull. Okay? They blend them together and then they put them between electrodes. And what they're hoping is that the red and blue separate from each other to form your red and blue separated, even though they were put together at once. Right? So think of it as you mix Red Bull and milk and then you cast it and you allow all the little droplets and everything else to form. Okay? The trick here is that I can't really control this. Right? I can't make a red dot here and a blue dot there. It's going to happen via thermodynamics. It's the red and blue separating from each other, in this case milk and Red Bull separating from each other, and I end up with a lot of these kinds of droplets. So all of those Kanaka devices I showed you, the purse and the bus stop, they're all actually made this way. And what they do is they do it what I call combinatorially. They try a whole lot of different ways of making the film and different ways of using slightly different Red Bull and slightly different milk to get the best pattern they can and the best efficiency they can. Right? But what we really want to do is to be able to control that pattern on this length scale so that we get the right pattern to get electricity out of the device. Okay? And the trick I use is to realize that that's about the same size as my polymer coil. So if I look at just this purple part, it turns out that this size is about 10 nanometers in real life. Right? So if I play correctly with the way this polymer chain demixes from the things around it, I may be able to get the right pattern. Okay? So mixing together red and blue, the way that company does it, is like taking these two chains, or milk and Red Bull, and these two guys want to separate, and they do it over a period of time. Right? You're seeing the Red Bull and milk get more and more separated from each other, but I can't really control its pattern. What I do in my chemistry and chemical engineering labs is I take these two chains and I attach them end to end. So make a chain that's half red and half blue. Okay? And let me actually make a few of these. If I have a container that contains a lot of half red, half blue block of polymers, the red and purple want to separate from each other. Pink and purple want to separate from each other, but they can't because I made a chemical bond between them. So the best they can do is create an interface between them, hopefully without breaking the chain. That doesn't happen in real life. Okay? And that's self-assembly, that the pink and purple want to separate, but I've created a boundary condition, a covalent bond between the two halves of the chain so they can't actually do it. This is called block copolymer self-assembly, and it turns out that if you play your cards right, you can make a red-blue chain If the red is much shorter than the blue, I end up with red spheres in a blue matrix. If I make the red a little bit longer, I can make red wires. These are 10 nanometers long in a blue matrix. In fact, I don't make them, they do it themselves. If I make it, and this is actually very intriguing, if I make the red and the blue close to the same length but not quite, I end up with what's called a plumber's nightmare situation. It's called a plumber's nightmare because it's bicontinuous. The red is connected all the way through, the blue is connected all the way through. If you're a plumber, you'd think this was a nightmare because you couldn't figure out which pipes were going where. Okay? And if the two are exactly the same, then I can make the stripe pattern. And we can put that together into a phase diagram. It's called a phase diagram because I can predict which phase, which pretty picture set of morphologies I'll get based on how much of red versus blue I put in and at what temperature, how much mixing I allow to happen. Okay? And so I can predict what kind of phases I'll be able to make. So it turns out that this strategy has actually been used a lot. So I'm trying to look for someone who has the very fancy sneakers. So the really fancy running sneakers like Nikes and Sauconys, all of those, they have really neat soles on them. There's a reason those guys are like $150. And the reason is that the soles are made out of these kinds of polymers because they've tuned the red and the blue so that they'll have the right mechanical properties. So the shoes keep their shape really well, but if you jump on them, they absorb the impact incredibly well. It's very different than wearing shoes like the ones I'm wearing, which just have rubber soles. Okay? So it's one way of getting really tunable mechanical properties. People are now using it to pattern a lot of other things. For instance, if I make a hard drive out of this, each dot is 10 nanometers big. And if I have a dot here and I know where they are, each of those can store 1 bit of memory. This is 10 to the 11 bits per centimeter squared. This is a lot of the technology that's going into flash drives and everything else. So you can store 4 gigabytes on a flash drive. Okay? A lot of what my group does is figure out how to apply the same self-assembly ideas to make conducting polymers and sometimes even biopolymers that have that kind of patternability and control over properties. Okay? So our strategy is this, that we take that polymer that absorbs light and we attach it to the polymer that helps pull the electrons off. We self-assemble it using the same things I just showed you, so that we make a bunch of different patterns, and then we put them between electrodes. Okay? And then frequently what we do is we play extra tricks to make the highways for the electrons and holes either go this way or this way, and try to understand how that geometry affects the way the device performs. Okay, so I want to give you some examples of how we do this. A lot of our work is at the arrows. How does a polymer that we make look like this self-assemble? Then how does a self-assembly affect the device? So I just wanted to give you a couple examples. So this is a polymer. I don't really expect you to know to even look at the chemical structure, but it has the thing that absorbs light on one side and the thing that pulls off the electron on the other side. What I'm showing you here is just that the block copolymer, that pink and purple thing I showed you that self-assembles, has a much higher current than the one where I just had 2 polymers separated from each other. All a higher current means is that I'm getting more electricity out of it. So just attaching the pink and the purple to each other has a huge effect on the way the device performs. And then the next thing I want to show you is that these guys self-assemble. So this is what's called a scanning probe microscope, and this is an electron microscope. When your picture is only 500 nanometers big, you can't use your eye to see it, you can't use light to see it, you have to use something much smaller. So here we're using electrons to see what the pattern is, and here we're using force. We have a very, very small nanometer scale tip that's going through and feeling the surface. Okay? And you can see what looks like a fingerprint pattern. That's the self-assembly. So I'm forming these little wires that are about 10 nanometers wide, and from the top they look like a fingerprint. And I'm going to compare something that's disordered, where the red and blue have completely mixed together, to something where they started to separate. That black-white line between these, that's the red and blue, right? In my life, they're actually black and white. And I'm going to compare that to one where I've got wires, right? And this is a cross-sectional view, so this is the bottom electrode. These are the wires. The wires are actually running parallel. They're running into and out of the screen, and this is the top electrode here. And I'm going to compare the way their devices work, right? So this is current, and this is voltage. And you see that the disordered material is terrible. It has a terrible voltage, short circuit current. We're getting like no charge out of this at all. It turns out that this one we worked so hard to make that had really long range order doesn't work much, much better. And it turns out this guy right here that had a lot of interfaces, but not terrifically good order, has the best short circuit current, right? And so this is part of, I'm showing you this partly because it's how science works. You make a prediction, you do an experiment, sometimes you get what you expected, and sometimes you get something slightly different, right? And then you try to go back and figure out why that happened. So in this case, once I actually look closely at this picture, I start to understand. If I have an electrode here and have a wire that runs parallel to the electrode, am I able to get power out of it? Right? I can't make power go this way because I don't have a highway for it. My highway's in the wrong direction, right? And that's the reason this material was quite so terrible, right? So what we're doing now is saying, okay, this might still be the best material, but we have to figure out how to make all of those wires connect the things we need them to connect instead of just running between them. And again, you have to ask yourself, how do I control something that's too small for me to touch and too small for me to see? And there are a lot of different techniques for doing it, involving playing with the surfaces you put them on, rubbing them to try and create a shear to force them to go where you want them to go. In our case, we really like using fields because then we don't have to touch them at all. So we take our materials and we throw them into a giant magnet, right? And what we hope is that the molecules all feel that magnetic force and get pushed in the right direction. And that's actually exactly what happens, is that we put this red-blue material into a magnetic field. It's pointed this way, and all of the red lines start pointing along that field. And then we can use, in this case we're using X-rays to show us which direction all the molecules pointed, and using that to optimize the devices. Okay? So I didn't want to go into too much scientific detail this early in the morning. I'm out of time. What I've tried to show you is that polymers and plastics are really everywhere, and they're incredibly useful. My children actually wore cloth diapers, and I've got to tell you that the plastic ones have significant advantages. Chemistry and physics are at the core of using and tuning them for any application, right? Everything I've told you about is some blend of chemistry in terms of making and characterizing them, and physics, right? These are not actually two separate subjects in my world. These are actually all mixed together. And there are a lot of new uses out there, ranging from lighting to energy generation. This is kind of an aside, but in order to do this kind of science, you actually need a fair amount of funding. In our case, it's federal funding, for the most part, because we need someone to help give us the materials and help pay people to help do the research. So we always end up thanking a bunch of different groups for helping pay for the research, right? Because we're not a company. And then who do they pay for? This is my research group. So the way science is done in the US and most of the world right now is as what one might call a medieval apprentice system. Right? So if you were going to learn to be a blacksmith in 1600, you would find a master blacksmith and go and work with him for a few years. That's how we do science. So most of these guys are graduate students or postdocs, and they work with me, and I help design their experiments and help analyze their data. We make discoveries together, and after a few years, they're pretty much ready to go off on their own and do my job. And some of these guys are now working for companies like Dow and DuPont, helping build these kinds of devices, and some of them will go on to be faculty and professors at other places. And this is what I'm not doing this morning. So thank you very much.